Hello everyone, my name is Connor Smiley, and in this video we're going to be taking another look at my AStar pathing implementation, but this time as engine programmers rather than gameplay or AI programmers, whatever jurisdiction you would consider AStar to be. So we have exactly what we had out of the box in last video. If you haven't seen it, I recommend checking it out if you'd like a comprehensive overview of my implementation. But if you're really just here as a performance junkie, then just follow right along. So we have AStar. The ghosts start out in the 4 quadrants of the screen, and I'm controlling the player with the yellow, and they smartly avoid obstacles. For example, whoop, I got stuck, so the pink and orange go to the right. Let's see if I can get them to repath around this blue island. So they're all heading upwards right now. If I jut downwards quick, the teal ghost just repathed. If you really don't believe me, go ahead and watch the full 20-minute video. I break it down line by line, and that's that. So now what we're going to do is examine my multi-threading implementation. So I'd like to preface this with, in the context of hobbyist projects or really just simple tech demos, I'm a firm believer that premature optimization is a sin, and especially since this is overall a single-threaded game loop, it's not really worth going to the trouble. I just did it for understanding's sake, and as you'll see in a moment, the right multi-threaded implementation does have significant performance benefits over single-threaded, but since this isn't a commercial application, the only purpose of multi-threading was really just to learn. So what we're going to do in order to benchmark this is we're going to multiply our ghost movement speed by an absurdly low value in order to keep them in their quadrants, which allows us to profile for pretty much the absolute worst case, consistently worst case. And I'm doing this rather than just calculating a path only to not translate the ghost by it, is to ensure that the compiler doesn't optimize out the logic without going to the trouble of viewing the disassembly. So, or disassembly, whatever. So anyways, we're going to rerun this demo, and we've got a reliable counter in the top left corner. If I was like working at a bigger company, I'd probably use an external tool to profile this, but given the quick and dirty nature of this demo, this is the best I've got. So this number is going to change in a moment. The render time is unaffected by our pathing. It's just the update time that we care about, so I'm sorry you have to squint at it, but here we go. So the ghosts are effectively staying put, and with a single thread, we're taking on average what I'd say is between 1 and 2 milliseconds. Again, sorry, those numbers are changing at the speed of light, but take my word for it, at least for example, 1 to 2 milliseconds. Now, if we go ahead and try what I would deem our better multi-threaded implementation, we can watch that number plummet. Oh, whoops. Or sorry, I changed that to 0. We're going to have the worst multi-threaded implementation, but doesn't matter. We're going to take a look at all 3, and then I'm going to explain my prediction on why things happen the way they do. So with this model, we're seeing numbers as high as 4 milliseconds per update, and it's all over the place. The point is that for some crazy reason, our performance is worse than single-threaded. Now, when we take a close look at the algorithm, the reason why that is as the name suggests, we're recreating a STL thread object every frame, and my estimation is that the cost of recreating this thread object actually outweighs the benefits that come with parallel computing. So despite allowing the pathing algorithm to take place at the same time as our player update and more importantly our raycaster update, which is a very expensive function. It's taking at least 0.1 milliseconds or whatever. It's taking at least half of the update time. The creation plus synchronization and even destruction of this recreated thread on a per frame basis is actually like way more costly. So instead what we want is to create the thread once and use some synchronization mechanisms to get much more juice out of our threading model, like so. Any second now. Okay. So now you can see we're consistently at 0.05 milliseconds per update frame, which is awesome. We're reaping the benefits of parallel computing as you would expect. I decided to draw the line at one thread because AStar, I'm sure you could parallelize it, use multiple threads to explore an open list and have atomic data structures like, lock-free queues or whatever. But if this was, again, a commercial application, you wouldn't be throwing more than one thread at pathing because the CPU is generally starved for threads, as there's a lot more important things that could take advantage of parallel computing. But either way, let's go over the preprocessor when it comes to this persistent threading. So basically, I use some atomics to ensure we don't run the pathing thread faster than we want to. And our only truly shared variable is delta time. So and of course, we're gonna just have a worker thread if we're not single threaded. No sense in the preprocessor is of course messy, but no sense in creating a thread that's just gonna idle indefinitely in the background. And again, of course, if this was a production quality or commercial application, we would simply pick the most intuitive threading model and stick with it rather than dirtying our code with preprocessor. But enough about that. So all we care about is the update logic here. So as I mentioned, if we're doing persistent threading, we want to share a delta time across our class so that we can, where are we using delta time? This might actually not even be necessary now that I think of it. Whoop. Okay, yeah, my bad. Yeah, we need delta time to spawn the thread, despite the fact that we were calling update goes with the local delta time member in the single thread model. But sorry, I'm already jumping too much. I've explained the recreate. This is a atomic synchronization Boolean, again, to prevent us from running the pathing helper faster than we want. But basically, of course, if this was single-threaded, we do it sequentially. We want to update the player before updating the ghost because they take the player into account. Raycaster is independent of pathing, thankfully, and again, we want to make sure we pass an up-to-date player regardless of our threading model. But let's take a look at how we spawn our persistent worker thread. So when this scene begins, we want to indicate that we're in fact gonna start our worker thread and we're gonna leave it running because we want to join on exit and we want to make sure we don't deadlock things. So that's why we need this atomic running Boolean. And simply while stuff is running, so we don't run into infinite loop, or even if the scheduler doesn't deadlock, it's just good to not even give the scheduler a needless infinite while loop in the first place. So if we're supposed to offload our pathing to the worker thread, if there's a need to update the path, we're going to go ahead and update it. Perhaps I could have more aggressively, like I could have had two timers going in parallel, but that seems needlessly complex if I wanted faster, like asynchronous pathing computation. But that's just, again, needlessly starving the CPU because we don't need more than one path per frame. So basically at the start of our frame, if we're using persistent threading, we're going to go and say to our worker thread, hey, whenever you're ready, I'd like you to please update the path. And then the moment this guy says, okay, I'm going to update that path for you, I'm going to say, okay, I won't update the path until you ask me to update another one, and go ahead and do just that. And of course, to be polite to the thread scheduler, we're going to yield because this is the worker thread. The main thread's got a whole bunch more cool stuff to do, like cast those rays and display them as vertical line segments. You've already seen this update ghost function. I didn't go crazy with read-write locks here. I think I was able to get away with just atomics. Generally speaking, atomics are more performant and, more importantly, more legible and just easier to reason about. So we are writing ghost positions, but that's okay to write ghost positions between... Actually, I think this is the only thread that writes to ghost positions, because we update the player and the raycaster, but this is the only point where ghosts matter. And let's see. This is bad that I'm second guessing my code mid-video. I might actually have a bit of a race condition here because I don't do any explicit synchronization between the end of the asynchronous ghost position update and the start of this collision check, which requires the ghost. But at the same time, this is not problematic because we're not going to get data corruption. In the absolute worst case, we're just going to read a slightly out-of-date ghost value. So in my opinion, due to the simple nature of this application, it's totally worth the risk of not cluttering our code even further. Although, again, if this was a larger code base, you don't want to have, invisible threading logic potentially mess up another programmer or even my own work in the future. So once again, thank you for listening. It's always fun to do multi-threading for learning purposes and actually reap some rewards. So goodbye and take care.